Welcome to this introduction to Explainable AI. The goal of Explainable AI is to enable transparent decision-making when opaque systems are involved. With opaque systems, we refer to those systems that involve artificial intelligence, machine learning, or decision services techniques. With Explainable AI, we aim at a fine-grained understanding of the rationale of specific predictions, so on a case-by-case basis. On the other hand, we also aim at a more coarse-grained understanding of the system's or model behavior. An interpretable system is a system that we don't need an explanation for. If we think about the mechanism of a bicycle, that's something that it's really transparent to us. Doesn't need much understanding from us to understand how it works. On the other hand, if we think about how the engine of a car works, that is on one hand hidden, and on the other hand, it's also more complex and less intuitive for us as humans. But if we think about opaque systems, there are actually different types of opaque systems. And the ones that are very important to deal with and to better understand are the ones that have an impact on the lives of humans. So if you think about the engine of a car versus the self-driving system of a car, the self-driving system of a car might have a much higher impact on the health of the people inside the car. So it's more important for us to be able to trust those systems that are more impacting for lives of humans. So this is the context where Explainable AI comes in to help. So what we want to achieve is to have predictive systems, predictive models that are trustworthy. And by trustworthy, we mean that we as humans are confident that the model will act as intended when performing a specific task that such a system was designed for. To reach those trustworthiness, we can either relate on transparent systems or on systems that are less transparent, so opaque systems, but we are able to generate an explanation for. So that's where Explainable AI is very helpful. So Explainable AI focuses on providing explanation of artificial intelligence-based systems, and techniques from Explainable AI can be used either to explain single predictions, like in this example here, or to explain, as we said, the behavior of a model as a whole, not just on a single input. There are actually different types of explanation. The most important are the local versus global explanations. So local explanations are used to describe the behavior of single predictions, whereas global explanations are explanations that target the description of the behavior of the entire predictive model. Another important type of explanations is the post hoc explanation, which is the one that involves an auxiliary method to explain a model that has been trained. Another distinction is between static versus interactive explanations. And the most common kind of explanations are static, but still there exist a few kinds of explanations that provide an interactive interface with the end users. One other aspect of explainability is the option to create surrogate models. So the explanation is not something like a different artifact with respect to the model, but it's actually a new model that is more interpretable with respect to the original one. Having seen different kinds of explanations, we can generate a small taxonomy. Saliency methods are local, static, post-hoc methods that generate explanations at feature level. So basically they generate sort of an importance score attached to each feature in the input for a specific prediction. Feature relevance methods are very similar to saliency methods, but they are global. So they are the global counterpart of saliency methods. So again, they expose overall feature importance measures for the model as a whole, not on specific predictions. Exemplar methods are local, static, post-hoc methods, but instead of generating feature-level explanations like saliency methods, they generate explanations by means of examples. And finally, knowledge distillation methods are global static post-hoc methods that generate a surrogate model, so a more interpretable model out of a more complex original model. Let's look at some examples. Saliency methods like LIME and SHAP explain the impact of each feature on a specific predicted output. So in this example, we have a model systems that predicts whether a certain user should get a credit card. In this specific example, the credit card was rejected for the user. And the explanation comes into the form of scores attached to each of the input features. And we can see that some of the features had a negative impact, whereas some of the features had a positive impact on the final predictions. However, the sum of the negative versus positive impact sums to a negative number, which is in line with the fact that the output was a rejection. So in this specific example, we can see that given the fact that the user has a specific age, has a specific value for the own car feature, and a specific value on the feature income, the system decided to reject the request. An example of feature relevance methods are partial dependence plots, and they explain the impact of features on model behavior. In this example, we have a student scoring system that uses historical data about students to predict the scores of a certain student on its first year on a given school. In this example, we are not looking at specific predictions, but rather we are looking at how the model reacts with different values of specific features. So this example, for example, is very important to understand that we see that the model is very biased towards, positively biased towards white people. On the right hand side, we can see that when the white feature is 1, so if the student is white, it is much more likely for the student to have a high score, whereas it is very likely for a non-white student to have negative scoring from the system. So it seems that the model is very unfair with respect to other classes of students that are not white students. So this is a very important concern with respect to the fairness of the model at hand. So this is a very powerful tool to identify whether systems like this can be used in production. Exemplar methods, an example of exemplar methods are counterfactuals, which respond to the question, what should I change in the inputs and how to obtain the desired output? So if we go back to the example of the credit card approval system, then the question becomes, how should I change my input in order to get the credit card? And if we remember, we saw that the age had a negative input, then maybe the explanation will be get higher age or something like that. So to summarize, explainability aims at increasing trust in decision-making processes where predictive models are involved. And it makes it easier to understand predictive models' behavior for end users. In addition, it can be very helpful for detecting biases and fairness issues in predictive models. The TrustyAI initiative, part of the Cogito project, contains tools and capabilities that aims at assessing the trustworthiness of applications for business processes that involve predictive models.